Good morning, everyone. I'm glad to be presenting here today and talking about our research on laboratory scale drill string vibration with realistic drilling fluid circulation. It was a great journey with my advisor, Dr. Al-Dushashi. Today, I'll start with a brief introduction to our engineering and scientific motivation, and that is where we found a key knowledge gap and how this discovery could help our industry. And then we'll talk about our test facility and our lab, and lastly, our recent findings and a glimpse into our future experiments. So motivation, the heavy bottom hole assembly, or the BHA of the drill string, is always active. That is, it's drilling. And it is a destructive process that generates a lot of chaos downhole. And we categorize this type of, any type of undesired and chaotic movements as axial, torsional, and lateral vibrations. So we map this, this is the axial, torsional, lateral vibration, and we map this based on the applied rotation and applied weight on bit. And we pray that we stay within that maximum RP region, and then we not stray away into the vibration zones and do not develop those vibrations to let the vibrations to develop into critical phenomena such as bit bounce, stick slip, or even whirling, which can be very detrimental to the downhole tools and the BHA and cost and the safety. But we found through our research, through our studies, that drilling fluids, the effect of drilling fluids on drill string vibrations has not been fully addressed. So the fluid is categorized as like a static, fixed damping variable, even though the drilling fluid is continuously pumped through the drill string from the surface and all the way it travels from downhole from the annulus section again. So on top, the fluid pressure, it's largely vary from the surface to downhole. So between the surface and downhole, there are limited studies to match the idea in the past, but none really took the time to make a complex experimental setup. Maybe it was too complex or difficult in the past. So we wanted to ask, does the drilling fluid affect drill string vibration dynamically? So is does it always damp the vibration, or can it also induce vibrations on the drill string? So we imagined our test facility, went onto the drawing board to make sure that our test facility would be field relevant. That is, anything we do with how we build, the results should relate to the field. So we took our time to mechanically scale the whole model. Then we wanted to make sure in the setup, all the drilling dynamics, that is rotation and weight on bit, will be applied, and that we can observe that. And of course, we should have realistic fluid circulation system, and that is, fluid should be pumping just as in the field, coming from the surface, going from the downhole and leaving in the surface. And lastly, with all these complex things happening, we got to have high frequency measurement to measure the vibration and movement of the drill string at every step. So we established our subsurface energy extraction and dynamics laboratory at Oklahoma State University. It was the first of its kind, and we built this first of its kind of setup, fluid-induced drilling dynamics test facility with realistic fluid drilling fluid flow. And the whole structure, that you can see, it's a transparent wellbore, and it houses the drill string that is modeled. Even though it's 25 feet long, the modeling, due to the downscaling, it represents a 300 feet long bottom hole assembly. And the whole setup is on a modular aluminum structure. That is, everything is kind of built like a Lego. It's the same piece, just built on top of each other. So we can easily change the setup, expand it, take it apart. So that was the big idea of making a modular setup. And we also need to make sure the whole thing is controlled, the data is collected, and the experiments is conducted just from the same screen, one single user interface on that desk. And we published our first paper at one of the AADE conference in 2023. So here's the schematic of it. On the left, that's where the downhole starts. We have the electromagnetic shaker that we give it the instructions to provide bit interactions and also the bit vibrations downhole. And we measure those vibrations responses on the BHA with triaxial accelerometers. And we also have multiple displacement sensors to track the movement of the BHA along the length. And then we have an encoder on the surface side that measures the rotation. And we also got a motor that is providing that rotation. And in line, we got that custom in-house designed fluid swivel to pump the fluid through the drill string, and the drainage system that collects and it brings back the fluid to the tank. So here are the photos. You can see on the left, there's the photo of the downhole system. You can see the shaker and all the wiring that goes into to instrument the setup. And on the right, we get the surface end where we get the motor up there, and in line, we recently put a torsional sensor to pick up surface torque. And then you get the massive fluid swivel and the encoder setup. And we got drainage system on both top and bottom to make sure that also the air and the fluid also like leaves together at the same time. And we are filled with this fully flooded, submerged drill string. And all the wiring that goes in, it comes to this one single terminal. There are about 22 sensors that go into monitoring the whole experiment and the whole setup. And there are also some other extra few communicators that are connected to the computer. And we observe everything from these two monitors in the on the desk. And the whole setup, all the data is collected synchronously. So everything is like on par with the time. And we collect the data at 10,000 hertz. So it's like every second, there are like 10,000 data points being created at the same time. And we're very fortunate to connect with Sunbeam Technologies too. They gave us this field sensor, and we're able to equip the setup with a field sensor that's been used during operations. And we tested and verified our setup. Are we really creating the drilling dynamics that we see in the field? And we published the data in one of the IPTC conferences that happened in Saudi. So coming to one of the recent findings, I'll share just a few recent findings that we have. So here we get a plot of PSD of the vibration energy over a range of frequencies. And all those lines, the blue and the red, represent the dry and submerged drilling. And the yellow and the purple represents two different flow rates and drilling with those two different flow rates, each one representing laminar and the second one is the turbulent flow. We find in the low frequency zones that laminar analysis flow, the yellow lines, you can see that it's way lower in the low frequency zones. And there are two plots. The first one shows when the drill string is subjected under a bit bounce, and the bottom plot shows when it's smoothly drilling. So in both cases, for free rotation, free drilling, and also with bit bounce, the laminar analysis flow is more effective in reducing low frequency vibrations, while turbulent analysis flow is more effective in reducing high frequency vibrations. So we find that just increasing flow rate doesn't decrease vibrations, but like how the behavior changes, how dynamic it is. And then we also looked at the lateral movement of the BHA to see the effects of the laminar flow condition and the turbulent flow conditions. And we find, yes, at the laminar flow conditions, the analyst effectively reduces the lateral motion way better because, again, the low frequency vibrations, that we can see. And turbulent analyst flow generates erratic lateral motion that hinders whirl development. And we saw less chance of whirl development with higher flow rates. And in these cases, we believe that those chaotic motions are also counteracting with the high frequency vibrations of the drill string. And what are we doing in the future? What we're doing currently is with my new hobby is drilling data analytics and machine learning. And we're trying to incorporate those into like improve the data to visualize the data better and really dig into what's going on. So you can see on the left, we get the unfiltered data. That is, this plot represents the vibration magnitude over the time of the test duration. And you can see in the unfiltered data, it's very hard to recognize what's really going on. But as soon as we filter it properly, we can point out. So the blue lines are the magnitudes, and we point out and mark the excitation zone when the drill string is excited with the shaker. That is the red. And the yellow is the damping zone. You can really clearly see the damping zone when we take out the excitation, and the free period in purple, marked with purple. And this filter data gives us this close view of the damping zone, and we're trying to quantify that. So the way we do it, as soon as we look at the filter data and we try to put an envelope fitted curve, we find that it is very close to vibration attenuation of underdamped vibration, and it fits with the logarithmic decrement, and with the exponential constant, the beta, it represents a decay rate. And from there, if we know the vibration frequency, which we do, we find out from data analysis, we can also find the damping ratio, which is universal from case to case. So if we have different drilling condition testing set up in the lab, and we're looking at the damping rate of it and the vibration characteristics of it, we'll always have this damping ratio that is universal to, and that is comparable to each other. So we can create all these different scenarios of drilling through different formations, and look at the vibration compared to each other on the damping ratio. Here I'll show you when we run the test and how it looks like in the lab. So everything is starts here at the desk where I control, and you can see the vibration, all the data being generated, that again, 10,000 data points at the same time. And here are the views. And this is the downhole side. You can see the shaker and all the instrumentation that goes in there to keep everything running and collecting all the data. You can see the BHA is whirling a little on some of the points. It kind of creates those vibration modes, so it's like it moves more at certain points. Then we get the massive swivel pumping the fluid through the drill string, the drainage, and the motor. And there's a tank. The fluid comes in, a closed loop system. And in the beginning, I mentioned that we got a modular setup. One of the great thing about that, we can keep changing it. So you've seen over the course, like we changed the design, changed the assembly 3 times, and it can see also the setup, it's angled in 10 degrees. So if you see the headline, we're looking at the effect of inclination. That's the recent thing we're working on, and hopefully we'll be publishing our findings at the next AADE conference. Thank you, American Association for Building Engineers, and y'all for listening. Yeah, feel free to ask any questions and reach out. If you don't get to, there's my email and LinkedIn too. Thank you.